Hello, my name is Ivan Curkovic and I'm assistant professor at the Faculty of Civil Engineering in Zagreb, and I will be presenting you the paper titled Behavior of Composite Plate Shear Walls with Variable Column Stiffness. Steel plate shear walls have been increasingly applied in structures as a lateral load resisting system. They consist of a thin unstiffened steel infill plate connected to vertical and horizontal boundary elements. Infill plates are very slender and they buckle under low lateral loads, due to which load-bearing capacity of steel plate shear walls relies on the formation of tension field. Contribution of the moment resisting frame to the strength of steel plate shear walls is completely ignored, and nominal load-bearing strength is calculated as the strength of the infill plate alone when tension field forms over the entire plate, as is given by the following equation. In that case, stress distribution between the system elements looks like on the given figure. It is clear that formation of the tension field requires boundary members of adequate strength and stiffness. To reduce these requirements, but also to increase entire system strength, ductility, and energy dissipation capacity, it is preferred to avoid plate buckling before entire plate yields in shear. This can be facilitated using thicker steel infill plates, using various types of infills, or by using numerous stiffeners, where all approaches imply significant increase in cost. An effective solution for infill plate stiffening proved to be the use of discretely connected reinforced concrete panels. Such systems were termed composite plate shear walls. In this case, nominal strength is at least 40% higher than that of steel plate shear walls and is calculated according to the following expression. The stress distribution which in composite plate shear walls is shown on the figure below. The design procedure for these two lateral load-bearing systems is based on capacity design approach, where the relevant member is either steel or composite infill plate panel. In steel plate shear walls, transverse forces are exerted onto boundary elements, which therefore need to have adequate strength and flexural stiffness. These requirements are usually easily satisfied for intermediate beams, where the stresses from the lower and upper plate mostly balance each other out. However, this is not a case for bottom and top beams, as well as for columns, which are exposed to tension field actions only from one side. Significant pull-in was noticed when steel plate shear walls were tested, and minimum requirement for column's second moment of area was prescribed, as given by the expression below. The same expression is applied on composite plate shear walls, although they have completely different load-bearing mechanism, where the infill panel exerts none or much less transverse force on the boundary elements. Therefore, this research was conducted to investigate the influence of column flexural stiffness on the overall behavior of composite plate shear walls. For that purpose, one-story, one-base specimens of quarter scale were designed and fabricated. The thickness of the steel infill plate was 1.5 millimeters, and it was welded to the fish plate over its entire perimeter. 50 mm thick reinforced concrete panel was used and was connected to the steel plate in discrete points. In order to simulate the use of prefabricated reinforced concrete panel, PVC tubes were placed along the bolt length. After concrete was cured, the tubes were pulled out, leaving small gap around bolt. Additionally, direct contact of reinforced concrete panel with boundary element was also prevented, leaving 30 mm gap around the reinforced concrete panel perimeter, which in previous research has been shown to enhance composite plate shear wall behavior, but is also necessary if prefabricated reinforced concrete panels are being used. Three different cross-sections of columns were used. Reference specimen had columns with a second moment of area, which corresponds to the minimum value provided in building codes. Two other column cross-sections were obtained by incremental reduction of flange width, which resulted in reduction of second moment of area by 18 and 36% from the reference column. Due to vertical placement of the actuator, specimens were rotated by 90 degrees from their true position within the structure. Specimens were bolted to the supporting reaction frame, which simulated fixed column base. Simulation of the out-of-plane support was carried out using lateral bracing truss. Loading of the specimen was carried out from one side only using a rigid adapter. Specimens were loaded in quasi-static manner using protocols of ECCS and ADC24. Displacement amplitude of each load cycle was defined using yield displacement, which was 3 millimeters, and was determined through preliminary numerical analysis. All tests were carried out up to the failure point or up to the point where specimen strength dropped to approximately 80% value of the obtained maximum strength. The obtained results regarding initial specimen stiffness, ultimate strength, and maximum displacements are given in the table below. In comparison to steel plate shear walls, initial stiffness was only negligibly affected by column flexural stiffness. This occurs due to the fact that steel infill plate increases specimen initial stiffness by almost 10 times when compared to the stiffness of pure frame specimens. As expected, ultimate strength of specimen decreased with the reduction of column flexural stiffness. After reaching ultimate strength, further increase of the displacement resulted in crack development at the corners of the steel infill plate, which propagated towards the plate center. Tension diagonals have formed only at infill plate corners, while the plate middle part remained almost intact. Final failure of the specimens occurred after the crack from the heat-affected zone at a connection between column outside flange and the base plate propagated into the column web. Failure of composite specimens started due to exceedance of the bearing resistance of the steel infill plate at a connection with the reinforced concrete panel. Although this failure mode was taken into account in the design process, it seems that prescribed approach is not valid for composite plate shear walls that have a gap between reinforced concrete panel and boundary elements. Such failure mode is not desirable for a couple of reasons. Firstly, inability to dissipate energy through damaging of reinforced concrete panel resulted in pinched hysteretic curves, which is more common for steel plate shear walls. Secondly, due to excessive widening of the bolt hole within the steel infill plate, additional hazard can occur due to reinforced concrete panel falling out of plane. All specimens have shown stable reduction of the secant stiffness up to a 4% story drift ratio, indicating that regardless of column flexural stiffness reduction, there were no negative effects on the overall specimen behavior under cyclic loading. In order to evaluate inward deflection of columns, LVDTs were placed along column height. Here, the displacement profiles of steel plate shear walls and composite plate shear walls are compared at 4% story drift. It can be observed that both specimen types show some amount of pull-in at their bottom part when compared to the pure moment frame specimens. Naturally, this is expected as transverse forces from the infill plate act on the columns. However, the amount of inward deformation is somewhat smaller for composite specimens. Also, there is almost no difference of the column pull-in deformation within the same specimen group, regardless of the used column cross-sections. In the first place, this indicates that the requirement for composite plate shear walls can be somewhat alleviated, but also, as all specimens show stable behavior up to 4% drift ratio, that the prescribed minimum column second moment of area value might be completely unnecessary. Hysteretic curves of steel plate shear walls and composite plate shear wall specimens were also compared. It is observable that composite specimens show less pinching in second and fourth quadrant as a consequence of reinforced concrete panel application, which prevents buckling of the steel infill plate and in turn allows for transfer of compressive stresses. Anyway, composite curves show more pinching than expected, which was the consequence of the steel infill plate bearing resistance failure. However, if energy dissipation capacity is calculated, it is clear that in spite of unwanted failure mechanism within the steel plate, a reinforced concrete panel increases the ability of the system to dissipate energy. Finally, it can be observed that addition of reinforced concrete panel increases initial stiffness by approximately 25%, while the ultimate strength is increased for about 10%. If the mean value of the difference between ultimate strength of composite and pure frame specimens, as well as between steel plate and pure frame specimens, is calculated, values of 203 and 170 kN are obtained respectively. This leads to the conclusion that influence of the reinforced concrete panel on the ultimate strength increase is approximately 19%. This is not in accordance with analytical values when real material properties are used. The above discrepancy of the experimental and analytical results is consequence of premature failure of the steel infill plate, which prevented complete yielding of the plate in shear. As the idea was to carry out further analysis of the column flexural stiffness impact on the overall behavior of composite plate shear walls, reliable numerical models were needed. For that matter, shell elements were used for simulation of the steel parts, and solid elements served for modeling of reinforced concrete panels. The steel reinforcement was modeled using smear concept, and connection between steel infill plate and reinforced concrete panel was simulated using beam elements. To further reduce complexity of finite element model, the reaction frame, out-of-plane support, truss, base plate, and rigid adapter were not simulated, but adequate boundary conditions were applied. As for constitutive models, we all know that steel does not behave in the same manner when exposed to monotonic and cyclic load. Therefore, cyclic stress-strain curves of steel were obtained using experimental monotonic tensile results using approach found in the literature. This constitutive model was applied for all steel parts except for the steel infill plate, for which it is assumed that due to its slenderness will not experience cyclic loading and compression beyond the elastic point. Additionally, within this approach, isotropic hardening was omitted because its influence on the overall behavior would be negligible when standard steel grades are used. Also, the failure of steel material has not been simulated. Concrete material model in compression before crushing was defined using multilinear isotropic model. To define concrete failure, this model uses von Mises yield criteria along with William and Warnke model. On the other hand, concrete tensile behavior was defined as linear elastic, having sudden drop in stresses when the failure surface is reached in one of the directions. For easier convergence, strain softening was applied, where after failure, stresses drop to 60% value of the tensile strength and afterwards gradually approach zero. Reinforcement steel used bilinear elastoplastic constitutive model with kinematic hardening. Finally, experimental results were compared with the numerical ones. As the simulation did not incorporate failure of the steel material, the results could only be compared up to a point when cracks start to open. In experimental research, this never occurred before 2.5% stored drift ratio, which also turns out to be the ultimate displacement limit according to Curkovic. As shown in figure, experimental and numerical results seem to compare well. Realized strength at 2.5% storage drift ratio is compared in the table, and high correlation of the results has been achieved, where high strength deviations exceed experimental results by only 1.7%. Finally, the following conclusions can be given. The experimental results show that reduction of column second moment of area by 36% did not have impact on composite plate shear walls ductility, as all tested specimens were able to tolerate stored drift ratios up to 4%. All specimens also showed stable secant stiffness reduction. Recorded inward deflections in composite plate shear walls were lower than the ones of steel plate shear walls, which confirms the premise that flexural stiffness requirements for composite plate shear walls can be less stringent. In order to increase energy dissipation of the composite plate shear walls, procedure for the design of the connection between steel infill plate and reinforced concrete panel has to be revised, particularly if precast, prefabricated reinforced concrete panels are used. Finally, the developed finite element models can reasonably predict experimental behavior and as such are reliable to be used for further numeric parametric analysis. Thank you for your attention.